more concrete, we have the k-median. That's the k-median objective. So as an example, we have the k-median objective, where we're summing distances between the points, we're summing the distances between the points at their assigned center. We want to minimize that. And as we said, because of the hardness, we can't actually obtain the optimal value, and we're looking for d hat, which is at most alpha times d, where alpha is the approximation ratio, and smaller alpha is a better approximation. And this is just to be concrete, I mentioned the k-median example. And also we have the fairness constraint. We've seen so many variants of fair clustering problems. To be concrete, we'll talk about demographic fairness, specifically the balance notion, where every cluster should basically mix the different colors, mix the different demographics according to some preset proportionality bounds. So concretely, for every cluster I, the cardinality of Ci is the number of points in cluster I. The cardinality of Ci blue is the number of blue points in cluster I, and we want the number of points, number of blue points in cluster I to be basically upper bounded by U blue times the number of points, and lower bounded by L blue times the number of points. So the number of blue points should be upper and lower bounded by specific proportions times the entire number of points in the cluster. And we want the same thing for C red, and we have different proportionality bounds U red and L red for it. Okay. Now, just the way we cannot get the true optimal value for the clustering cost, we also are sometimes unable to precisely satisfy the fairness constraints. And in fact, with the two-stage approach, we mostly end up violating them. So we end up with the guarantee of the following form. So you have the same guarantee, Ci blue is lower and upper bounded, but instead of being upper bounded by U blue times Ci, we relax it a bit. So we add delta, where delta is strictly greater than 0. So this is basically enabling larger violations. It's a small violation of the upper bound U blue times Ci. And similarly for the lower bound, instead of L blue times Ci, we subtract delta and basically allow a smaller lower bound. And similarly for the red color as well. Okay, so there isn't a single approach to solve all fair variants, and that is not surprising because, as we said, fair clustering is really mostly constrained clustering, and constrained clustering has been, introduced and studied before fair clustering, and there isn't really just one generic approach to solve all constrained clustering variants. The second thing to mention is the same problem may actually be solved using different algorithms, and we may even desire different algorithms to solve the same problem. So, for example, we might have two algorithms, A1 and A2. Algorithm A1 could have a higher clustering quality, that is, it does a better job in minimizing the clustering cost than A2, but A2 could have a faster runtime. So we might want to use A2 at times instead of A1 because it just simply has a better runtime. Now, as we spoke for the center-based clustering paradigms, the K-center, K-median, and K-means, we have the two-stage approach, which is a simple approach with many applications. That is, it was able to solve a large collection of fair clustering problems. So how does the two-stage approach look like? Well, it consists of two steps. In the first step, you open the centers, you basically decide the centers. You do that by using a fairness agnostic clustering algorithm. So for example, if you have the K-means clustering objective, you just go ahead and use a regular K-means approximation algorithm to decide the centers. This will end up giving you a collection of centers S. And the more tricky step is step 2, where you basically have to post-process the assignment function. So in step 2, you have to process the clustering to satisfy the fairness constraints, and you have to do this at a bounded increase to the clustering cost. Mostly this means that you're going to use a linear program, although there are other methods to do that as well. Okay, so we will consider as a concrete example, like we said, the group or demographic fairness, where every cluster is supposed to mix points of different colors. So on the left, we have the agnostic clustering, the clustering which doesn't take into account fairness. We're just minimizing the K-median objective, and you might end up with clusters that look like this. They don't mix the colors. On the right, we have the group fair variant, where we basically, again, have the same objective. We're minimizing the clustering cost, but we have this constraint, which actually is telling us to mix colors, mix points of different colors in each cluster. Okay. All right, so let's just see how the two-stage approach runs. So let's say that we have this given instance. Clearly, the color agnostic would lead to the output on the left, where the clusters don't mix the colors. Now, step one says what? Just run a regular clustering algorithm to choose the centers, and we did that. So we are doing two clustering. We chose to let k equal to 2. We ran the regular clustering algorithm, gave us two centers, C1 right there and C2 right here. Now the centers are open. The question now is how to assign the points to the centers. If we were to just minimize the cost, we would get an unfair solution. So if we were just to minimize the cost, then we would assign each point to its closest center. And this clearly leads to basically an output that violates the fairness constraints. The colors don't mix. So how do we satisfy the fairness constraint? We can build an integer program, specifically this following integer program. So the integer program saying minimize the clustering cost, d of I and j, xij over the centers and the points. Okay, so to be more clear, what is xij? So xij is a decision variable. It's equal to 1 if point j is assigned to center I, else it's equal to 0. Now keep in mind, at this point, the centers are decided. We know what the centers are. What we don't know is how the points are going to be assigned to the centers. So we set up this integer program, which says minimize the clustering cost, okay, subject to the following constraints. Now let's go through the constraints. The first constraint is just saying that xij should be either 0 or 1, as we said, by construction of xij, it's equal to 0. If it's not assigned, if point j is not assigned to center I, it would be equal to 1 if point j is assigned to center I. The second constraint says the sum of xij, we were to sum over the index I, we should get 1. And concretely, we have two centers, C1 and C2. If we were to expand the sum, it's saying that x1j plus x2j equals 1, which is basically, in words, it's saying basically point j should either be assigned to center 1 or center 2. That's what the constraint is saying. And then we have these four constraints, which are actually the fairness constraints. They're basically just enforcing proportionality. So they're saying, so right here, consider center I, we're summing over all of the points j. So this is equal to the total number of points assigned to center I. And it shows up again here, actually. So this is again the total number of points assigned to center I. This is the upper proportionality number, and this is the lower proportionality factor. And in the mid, we have the total number of blue points assigned to cluster I. So what this constraint is saying is that the total number of blue points assigned to center I should be upper and lower bounded by the proportionality bound, U blue and L blue. Similarly, we have another bound for the red color, all right? And these two constraints are actually for center 1. That's why you see x1j, all right, throughout. And this is again the same color proportionality or fairness constraint for the second center, C2. And here you see x2j instead, okay? So we basically, so it's very clear that this, since it's minimizing the clustering cost, this is basically an optimal solution. And it's also clear from the constraints that it would also be a fair solution. You have it right, minimize the clustering cost here, and it's basically satisfying the fairness constraints here. Now the problem is that integer programs, it's an integer program. Integer programs in general take exponential time to solve. So the way to deal with that is to simply relax the program. So instead of saying xij is either equal to 0 or 1, we say xij lies between 0 and 1, and we end up with a linear program. And we know that we can solve linear programs to optimality in polynomial time. So now basically we can solve this, this program to optimality in polynomial time. Now the problem is that the resulting solution xij is possibly fractional. So that means that xij is neither 0 or 1. And that basically doesn't have an interpretation because xij should either be 1 or 0. 1 means assigned to the center, 0 means not assigned to center. So, you know, between 0 and 1 is not something we can basically work with. So what we do is that we apply a rounding technique, xij, to make Xij become integral. So I'm not going to go through the rounding technique because they tend to be the most difficult step in actually the entire algorithm, and they're application dependent basically. But to some, basically, you will apply the rounding technique, and then you'll end up with this solution. So instead of actually ending up with clusters that are either completely blue or completely red, you'll end up with clusters that mix the two colors. Now, the choice of rounding technique, as we said, is non-trivial, and often it's the most difficult step in the algorithm. So the previous work on demographic fairness actually follows a very similar sketch to what we had mentioned. They mostly differ in slight details in terms of writing the LP, because they tend to have slightly different objectives. They also differ in the application of the rounding techniques, but they're all based on basically constructing an LP to assign the points to the centers. But I just want to highlight other post-processing approaches for different problems. So, for example, the recent paper by Chakrabarty and AI Stats of 2022 on alpha equitable fairness uses a combinatorial approach that is not LP-based. There's also the work of Brubach and ICML on pairwise fairness, which uses a randomized approach, again, not LP-based. So the post-processing approach doesn't have to be LP-based, although mostly it is. Okay, that's all that I wanted to say about this.